Well, good afternoon, and so in this lecture, what I'd like to do is we will start a unit on removal and control of primary particulates. But I think it's very important for you to understand what we're really talking about and the importance of removing these primary particulates. We're talking in many cases about combustible dust. And while it may just seem that dust is essentially that material that collects, for instance, on your furniture or in quiescent corners of your room, under your bed, we're talking about a much more insidious hazard, as is mentioned here. So what I'll be doing in this lecture is initially we'll look at a number of little video clips from the Chemical Safety Board video about combustible dust. So in this first video, what I want you to do is just watch it and think about what we really mean by combustible dust, and think about the importance of controlling this combustible dust. Some of you may end up working in an environmental health and safety role within a manufacturing facility. So it's really important to think about what this means and how this impacts the lives of workers and also their families.
911 emergency.
I need 8 units, sugar fighting now. It's just blood. It's just blood. I need all 5 units to the sugar refinery now. It's on fire. It's blood.
At 7:15 p.m. on February 7th, 2008, a violent explosion erupted at the Imperial Sugar Refinery in Port Wentworth, Georgia, just outside Savannah. Surveillance cameras in the area captured the blast, which took the lives of 14 workers and injured 38 others. The Chemical Safety Board launched an investigation. The fuel for the blast? Combustible dust.
Combustible dust can be a catastrophic hazard in American industry. 3 of the 4 most serious accidents that we've investigated have been combustible dust explosions.
In 2006, this pattern of accidents spurred the CSB to issue a comprehensive study of combustible dust, which uncovered 281 fires and explosions that had occurred over the previous 25 years. The study revealed what the CSB called a significant industrial safety problem. Combustible dust fires and explosions continue to occur frequently, fueled by accumulations of combustible dust, which can gather over years in hidden places or in plain sight.
No company wants to see its facility blown up and destroyed and its employees killed, but they just don't understand what the hazard is. They don't realize that they have a hazard here until that one day when the explosion occurs, and it's a terrible tragedy for them. And they look back and say, if we'd only known.
This next video is a description of a case study. It's actually an event that occurred in an aluminum processing facility for auto parts. A number of things I want you to look at in this next video. One is look for the drop box. We'll talk later in this lecture about drop boxes, which are basically a gravity settling unit. So look for that in the video. To the left of the drop box, there's actually a centrifugal separator. Talked about a dust collector, but that's what that is, and that's used because it's much more efficient at removing smaller particles than is the drop box. So note that. And then the other thing is note the way that the fireball propagates through the vent. It really is a demonstration of plug flow. You can actually see how it moves sequentially through the venting system, and then ultimately it does move out into the room. So think about that as you're watching this next video.
When Tammy Miser got a phone call late one evening in 2003, she worried it would be about her brother, Sean Boone, who worked at an automotive parts factory.
There had been an accident there before, so I knew.
Sean Boone was a mechanic at the Hayes Lemmers plant in Huntington, Indiana. The company produced aluminum car wheels. The process of finishing the wheels left behind aluminum scraps, which were chopped into small pieces and sent to a furnace to be melted and reused. Chopping, drying, and blowing the dry chips through the transfer piping created highly combustible aluminum dust, which flowed through ducting to a steel drop box outside the building, where large particles were trapped.
So I just want you to look at this. These are actually two of the types of units that we'll look at this week. The first on the right is the drop box. So you've got higher concentrations of large particles, and that's what you're removing into the hopper that you can see just below it. To the left would be a centrifugal separator. We'll talk about those on Friday. And those are used because they're much more effective at removing smaller particles.
The air then entered a dust collector, which removed finer aluminum particles. Over time, aluminum dust accumulated inside ducts. In addition, there were leaks in the piping used to transfer aluminum chips, which caused dust to build up on surfaces throughout the furnace area. Aluminum dust landed on beams, ledges, and equipment. In some places, the dust was several inches deep. On the night of October 29th, about 10 minutes after workers started the aluminum chip melting process, aluminum dust inside the dust collector was suddenly ignited, perhaps by a metal ember or impact spark, resulting in a large explosion. The blast propagated back through the duct into the steel drop box, blowing it apart. The fireball and pressure wave continued back through the ducts.
So watch this. We'll talk about plug flow in a bit, and what you actually see is as you can watch the fireball propagate back, you can see it actually moves sequentially. So essentially it's moving as a plug flow system back through the pipe. So think about that as we talk later about plug flow systems.
Into the building, gaining intensity as the accumulated aluminum dust ignited. The violent disturbance shook loose dust that had built up on external surfaces. At about 8:30 p.m., plant mechanic Sean Boone was one of several workers in the area of the furnace. Without warning, a fireball erupted from the furnace, engulfing the area and igniting airborne dust in a second, larger explosion. The explosion blew a 50-foot wide hole through the roof of the building. Co-workers found Sean Boone lying on the floor near the furnace, gravely injured. He was rushed to the hospital and put on life support.
So in that last video, you saw the gravity of the situation with combustible dust. It's mentioned that was in a auto parts manufacturing facility. The first one was in a sugar processing facility. There were numerous industries where combustible dust can be an issue and can be catastrophic. Another issue with combustible dust or primary particulate is that many of these materials can be toxic. We looked at issues related to silica and asbestos back in the respiratory system. So there, how those particulates are toxic, can cause fibrosis of the lungs. We also looked at a number of other issues. For instance, the way PAHs and other carcinogenic compounds can sorb or attach to particulate matters. And then if those particulate matters are respired, they too can cause cancer because of those carcinogenic compounds. So many of these combustible dust materials, the primary particulates, can be small enough to be respired. In this next video, what I want you to do is look at that, thinking about what this really means, or what the situation really means to the workers in this environment, and what impact it may have on their health and well-being.
West Pharmaceutical made small rubber medical products, such as syringe plungers and stoppers, at a large manufacturing facility with nearly 300 workers. In the process, large batches of rubber were compounded and rolled into long strips. To keep these strips from sticking together, they were dipped in a vat containing a whitish slurry of water and finely powdered polyethylene, a petroleum-based wax-like plastic. The coated rubber strips were then blown dry with fans and folded for later processing. As the rubber sheets dried, combustible polyethylene dust, which was not visible to workers but is colored white here for illustration, was blown into the air.
So if you watch the rest of the video, the link is right here, you'll see how critical this situation became to these workers and the impact on their lives. But all along, this dust from the polyethylene powder was in the air. They were breathing that, and there could be a significant potential impact to their health and well-being because of that.
West Pharmaceutical
So in this next clip, what I'd like to do is look at why combustible dust is so highly flammable and explosive. So this gives some demonstrations that really does show the flammability of this dust.
What is so frustrating about dust explosions is that they're so preventable. And I believe that one of the reasons that dust explosions continue to occur may simply be a lack of understanding about the materials. Most solid organic materials will explode if the particles are small enough and they're dispersed in a sufficient concentration. Some of the materials that could form combustible dust, and there are lots of them, could include coal, sawdust, food products like sugar and flour, pharmaceuticals, many chemicals, and even many metals.
Like all fires, a dust fire requires fuel, oxygen, and an ignition source. A dust explosion requires two additional elements: dispersion and confinement. The CSB commissioned laboratory tests using a sample of fine polyethylene dust found by investigators in the rubble of a North Carolina factory. Dust is dispersed into a flame, creating a fireball. When the dust is confined within a structure or a piece of equipment, a powerful explosion can occur and propagate, as this coal industry video demonstrates. Dust may accumulate on surfaces and lie undisturbed for years. Then some initial fire or explosion, known as a primary event, shakes it loose and ignites it.
It
causes a pressure wave to go through the plant, and that dislodges all of the dust that is perhaps unknown up on the rafters, on the beams, on the tops of equipment, and that serves as the fuel for the secondary explosions that move through the plant.
Most of the fatalities and the devastating injuries have been caused by these secondary dust explosions.
According to the NFPA, a catastrophic explosion can occur from as little as 1/32nd of an inch of accumulated dust, around the thickness of a dime, covering just 5% of a room's surface area. The NFPA therefore recommends that companies control fugitive dust emissions, design facilities to prevent dust from migrating and accumulating, and perform rigorous housekeeping to remove any dust that does build up.
So in this next part of the lecture, what I'd like to do is start looking at the control of primary particles. When we talk about controlling primary particles, the type of devices that we typically use are divided into two types. The wall collection devices, that is gravity settlers, cyclone separators. You saw the two of these in the one of the previous videos, and electrostatic precipitators. Smaller particles are removed with dividing collecting devices, and these include filters and scrubbers, and we'll talk about that in the next few weeks. Now, one of the things to recognize about these wall collecting devices is basically what we're looking at is particles migrating towards a wall. They hit that wall. In some cases, they will actually aggregate, so they combine together to form a larger particle. They are then collected, typically fall down to some sort of a hopper where they're collected and then disposed of. Gravity settlers are used because they're simple. They can be mechanically cleaned. They require very little maintenance, have low capital cost, low energy and maintenance costs. They don't require a significant amount of energy, and they're reliable predominantly for these larger particles. Now they tend to be large, and you'll see this with the gravity settler that we will look at designing. And they tend to be used for very dirty gases. You saw that in the video. They were used for pre-treatment prior to the cyclone settling. Now here is an image of a gravity settler. So what we have is a couple things to note is that the cross-sectional area of the duct that through which the air flows is significantly smaller than the cross-sectional area of the actual drop box. So what we have a significant slowing of the gas as it moves through the drop box. Typically we will also have some sort of a baffle mechanism here, and that's to try and distribute the flow so that it's distributed across the vertical profile of the drop box. Shown here is just another image, much more like the drop box you saw in the image. You can see the picture here. Again, typically what you're looking at is a dust-laden stream, so significant concentrations of particulates, the chemical, so that gas moving into this large area, slowing of the velocity. The particles then are collected, and then they are discharged to a waste, and then typically then that airstream goes on to a secondary treatment process, referred to in this case as a dust collector. That's what it was referred to in the video, and there it was a cyclone settling unit. We can draw a gravity settler simply as a long rectangular box. So we'll draw that here. And we have flow in and then out the other end. Now, the horizontal velocity we will describe with the term V average. So that's our horizontal velocity, and that is equal to the flow in divided by the width times the height. We'll talk about VT shortly. Our assumptions here are that the flow is plug flow, so we'll describe that as, so we have a plug of air moving down through the drop box. So this is moving in, and it's moving in the x direction. So it moves as a parcel, okay, down the drop box. We'll also assume that this V average, in some cases this is referred to as V naught, and we'll assume that that is constant everywhere in the chamber. Now the vertical component of the velocity of the particle is the terminal settling velocity. So that's the velocity of the particle when the drag, the buoyancy, and gravitational forces are all balanced so that the acceleration of that particle becomes zero. So this is the vertical component, and that is referred to as V sub t. Now we'll also assume that if a particle settles, it's not re-entrained. So once it hits the bottom of the drop box or the gravity settler, it remains there. It's not re-entrained into the airflow. Now, as the particle enters the chamber, it will enter at some distance h above the floor, and the time that it takes for that gas parcel to traverse the chamber is referred to as T sub gas. So that's our time that it takes for that parcel to move through the chamber. And that is equal to L over V sub average, or as I mentioned, that's V naught. Now the time that it takes for the particle to settle is H over VT, so the height divided by the terminal settling velocity. We can describe this drop box in this way here, where what I've done is I've shown the particle movement through the chamber. So it would take the V average, VT, and combine those. We have a diagonal line showing the movement of the particle. Now the purple lines, as you'll see, the slope on all of these are identical. The only difference is really where that particle enters. And you can see by the purple lines that those particles escape from the drop box, so those will not be collected. On the other hand, mark these with an X, the red particles, shown in X, all are captured. So if we, same slope, trace that line, and these particles hit the bottom of the collector and therefore are captured. Now we said we had the time for the gas to traverse, and that's our we're using our horizontal velocity. And then we have the time for the particle to traverse. There we're using the settling velocity. If we take the ratio of those two, then what we determine is the efficiency of removal. Now I'm not going to go into the details in terms of how we derive these. There is a reading on Kappa if you wish to take a look and go through the whole derivation of these equations. As I mentioned, this equation describes the efficiency of removal. We are assuming plug flow through this gravity settler. Now remember, we also said that we're assuming that these particles are uniformly distributed. So as they enter, they are uniformly distributed across the inlet. We'll also assume that they do not interact with one another. So we have no aggregation, we have no particle size growth in this reactor. And we can use Stokes' law to calculate the terminal settling velocity. We will assume that we have spherical particles and laminar flow. And that's important in terms of the calculations that we will do as we move forward. Now note from here, this first equation does subtract the density of the air from the density of the particle. However, when we're dealing with air, the density of air is so much smaller than the density of the particles. For the most part, that is typically ignored in the efficiency equation. Now, we also can use a mixed flow model, and this assumes that we have complete mixing in the Z direction, but we do not have mixing in the X direction. And if that is the case, then the efficiency will decrease, and we can use this equation here. So this is the efficiency of the mixed flow model, and it is equal to 1 minus E to the minus efficiency of the plug flow system. Now, gravity settlers are typically used with particles that have a terminal settling velocity greater than about 13 centimeters per second. Most commonly, they're used for particles greater than 100 microns in size. However, they can be used for particles greater than 50 if the density is relatively low, as shown here, or even greater than 10 if the density is high, so around 3 grams per cubic centimeter. So that's about the density of sand. Gas velocity needs to be uniform. Usually it is within 50 to 250 centimeters per second, although less than 30 is best for high efficiencies and also to prevent re-entrainment as those particles actually hit the bottom of the collector. Now we want to operate in laminar or transitional flow regime, so the Reynolds number needs to be less than 2,000, 2,300. And we can use this equation here to calculate the Reynolds number of the gas. So we're looking at the Reynolds number is equal to the density of the gas times V average times the height of the collector divided by the viscosity of the gas or the viscosity of the air. Typically, we're working with air. Okay, so let's look at this first example. We have a gravity settler operating at ambient conditions. It has a height and width of 3 meters and a horizontal gas velocity of 20 centimeters per second. First thing we want to do is determine whether or not the airflow through the settler is laminar or turbulent or transitional. And we'll assume that the room temperature is 20 degrees, so we have a dynamic viscosity of 1.86 times 10 to the minus 5 kilograms per meter second, and its density is 1.18 grams per cubic meter. So let's just write down our parameters. We have volume is equal to height, equals 3 meters. The average is equal to 20 centimeters per second, which is equal to 0.20 meters per second. So the Reynolds number for the gas is equal to the density times V average times the height divided by the viscosity. And that is equal to 1.18 kilograms per meter cubed times 0.2 meters per second times 3 meters divided by 1.86 times 10 to the minus 5 kilograms per meter per second. And that is 3,850. So this is turbulent. So we've got turbulent flow here. We want R sub E to be less than 2,000 for effective operation. Some texts will say 2,300, just somewhere between 2,000 and 2,300. So what do? Well, we can reduce the velocity. And if we reduce the velocity to 0.01 meters per second, or 1 centimeter per second, that yields a Reynolds number of 1924. So at that point, we've met this criteria. The problem is that we've got a very, very low flow rate. For the given size, at a flow rate of 0.01 meters per second, sorry, at a velocity of 0.01, so that was our velocity, multiplied by 3 meters. By 3 meters, this gives us Q, and this is 0.09 meters cubed per second. So this is extremely low flow rate. So this is our Q. But in all practicality, this is extremely low. We could triple the width. So we could make that 9 meters, but we'd still only be at 0.27 meters cubed per second. And often we're looking at treating flow rates on the order of about 6 meters cubed per second. Now, if the flow is turbulent, then you want to use the hydraulic diameter. So the equation for the hydraulic diameter is 4 times the cross-sectional area divided by the wetted perimeter. And for a box, we have here the equation for the hydraulic diameter. Now we can take this another step further, and we can look at determining the length of a gravity settler required to obtain an efficiency of 90% when we're collecting particles 15 microns in diameter. We have a density of 2.0 grams per cubic centimeter for the particles. We'll use the velocity that we just calculated and the chamber sizes that we just used. And again, we'll assume that the settler is operating at ambient temperature and pressure. So again, we'll need to use Stokes' law, which we mentioned before. So V sub T is equal to 9.8 meters per second squared times 50 times 10 to the minus 6 meters squared times 2,000 kilograms per meter cubed divided by 18 times 1.86 times 10 to the minus 5 kilograms meters seconds times the absolute viscosity, and that is equal to 0.146 meters per second. Now, this equation assumes laminar flow. If we have transitional flow, the coefficient of drag is equal to 24 over the Reynolds number, and you want to use the Reynolds number and to calculate the coefficient of drag, and then use the equation 4g times the diameter of the particle times the difference between the density of the particle and the density of the gas or air divided by 3 times the coefficient of drag times the density of your gas or air to the 1/2. So if you have transitional flow, you'll want to use that equation. Let's check the Reynolds number of the particles. And that is equal to diameter of the particle times the terminal settling velocity times the density of the gas divided by the absolute viscosity of the gas, and that is equal to 50 times 10 to the minus 6 meters times 0.146 meters per second times 1.8, let's erase that, 1.18 kilogram per meter cubed divided by 1.86 times 10 to the minus 5 kilograms per meter second, and that is equal to 0.7, which is less than 2. So the Reynolds number of the particle being less than 2 shows that we have laminar flow. The length is equal to the efficiency times H times V average divided by VT. So all I've done is rearrange that previous equation. Since we want N equal to 0.9, so the length is equal to 0.9 times the height, 3.0 meters, times V average, 0.01 meter per second, divided by 0.146, and that is equal to 0.18 meters. It's not very long, but remember, we're only treating a very, very low flow rate. And finally, we can determine the length if we were to have mixed flow. Remember, the equation is the efficiency is equal to 1 minus exponent of the efficiency for plug flow. So this is our mixed flow model. And this is 0.9 equals 1 minus the efficiency, and that is equal to minus VT L over V average times H. So Ln of 0.1 is equal to minus 0.146 meters per second times L, which is what we're looking for, divided by 0.01 meters per second times 3 meters, and this is equal to 0.47 meters. So we need about a half a meter here. But again, remember, in our calculations, our flow rate was only 0.09 meters cubed per second for this situation. And finally, you can use this figure here to estimate the terminal settling velocity of a spherical particle. And finally, this lecture should help you understand the importance of primary particle removal or dust removal, and how to design a simple gravity settler or a drop box. Thank you and have a great day.